Welcome back. Today we're going to be looking at one-to-one functions and inverses. Get started because it's kind of a longer one. I'll start with our creed. Don't forget, you say the creed, you pass the class. You don't say the creed, you probably don't pass the class. Today's a new day. I can read and remember well. I can develop my viewpoint and apply it correctly. I have eyes to see, ears to hear, and a mind to understand. It might not be easy, but it's worth it. All right, let's get started with one-to-one functions. So, in order to have an inverse, this whole thing we're talking about, you have to have a one-to-one function. So the first thing to ask yourself is, well, what's a one-to-one function? Well, we know what a function is, right? This is the one thing that I try to drive in all the time, is that a function takes some x, funnels it through some system. It could be super complicated. It could not be complicated. Sometimes it looks like that machine we saw, like this. Sometimes it looks like a formula, f of x. Sometimes it looks like y equals, but it takes some x number and funnels it into some other y number, right? Or some other f of x. A function takes some number, funnels it through a system, and it turns into another number. Well, one-to-one function says, hey, we're going to do that, and we're going to put one extra condition on it. We're going to take some number, call it 4, call it 8, call it 1 million, or 1,000, and we're going to funnel it into exactly one other number, right? So 4 turns into 10, 8 turns into 7, 1 million turns into 2. Doesn't matter. We're just doing a one-to-one function. This function defines those x's into a specific y value. Now, the reason it's one-to-one is because what we're not going to do is say that more than one y value can be given from x values. So we're not going to allow, I'll do it in red and then I'm erasing it. We're not going to allow some 10 to also turn into 10, right? So you think like, oh, when would that ever happen? Well, if you think of a parabola, like the most basic, not one-to-one function is a parabola, the normal x squared parabola, right? And you think about the number of 2, what does 2 turn into? 2 squared is 4, right? Well, what does negative 2 turn into? Also 4. So that function's not one-to-one. It doesn't do what we just said, but it's still a function because it absolutely still passes that vertical line test that we've talked about, if you see that line moving through. So that's the difference between a function and a one-to-one function, and you'll see it play out. I know that's a real quick definition, but you'll see real fast as we start moving through it. Oh, that makes sense. So the way we check for it, the most common way we check for it, is this thing. We've already learned about the vertical line test. It's just a horizontal line test. You run your pin or a horizontal line through the function down, and eventually you see, does it hit a point twice, the function twice in the same y value, or does it not? So let's find out. Now it says use the function and a graph to determine whether these functions are one-to-one. So I'll start with the graph because I prefer it. But if you prefer the function, we'll look at that as well. So here we go. We've got a graph. You know, this is one of the things, if you go back to day 2, you can kind of see there was a chart. If you look at lecture notes, the second day of lecture notes, there's a chart with all the parent functions. That's our x cubic parent function, right? So I'm going to take this purple, and I'll do it in blue. I'll do it in green. I'm going to take this green line, right? And I'm going to draw it over here. I'm going to say, does this green line ever touch the function twice in the same y value? Does that green line ever touch the red function twice? Not so far, and if it were to keep going forever, I don't think it ever would. So what that says is not only is this a function, so f of x, check for function, but it's also a check mark for one-to-one. Okay? That's using the graph. That's using the parent function graph that we know. And we learned last week that you can apply transformations to functions. So if you had a non-parent function, you could apply those transformations and try to see what you think about the graph. And then it says, okay, well, let's use the function then, right? Let's use the function and the definition to kind of determine whether or not it's one-to-one. Well, if we got x cubed is kind of like the first function, the first exponent function, right? Where that negative sign really matters, right? So let's just think about what's f of 0? F of 0 is 0 cubed and it gives you 0, right? All right, cool. Well, it looks like that thing never turns around on the negative side. So what about f of negative 1? F of negative 1 is probably going to give you negative 1 cubed, which is Negative 1 times negative 1 times negative 1, which stays negative, right? So for every negative number, we know, and we've proved this already in class, that f of negative x is the same thing as f of x, right? Because it's an odd function. Nope. Yeah, that's right. Is that right? No, I forgot the negative sign on the outside. Sorry. F of negative x is the same thing as negative f of x because it's an odd function. So if we're looking at this function, we're saying f of negative x, if it throws the negative on the outside, then f of negative x is never going to be the same thing as f of x, right? Because it can't be. So what we're looking at here is saying that, and this is just a long way around saying that f of negative 1 is not going to be the same thing as f of 1, right? So this function is different in the positive and different in the negative. And if we wanted to go ahead and define we did. If we want to go ahead and define those not as 1 and negative 1, but as x and negative x, we'll see that as we keep going, they'll never be identical. Though the numbers will be identical, the absolute value of those numbers will be the same. The numbers won't be. So it passes the horizontal line test. It's 1 to 1. Let's look at one example where it does not pass this function, right? Take that same green line, boop, put it over here. I only have, boom, I see right away, right? I'm going to draw big green dots. Boom, boom, hits the same spot. I know right away. F of x is not 1, 2, 1. Right? Awesome. I'm going to leave that there so we can see it. F of x is not 1 to 1 because it does not pass the horizontal line test. But let's just pick two numbers to find out. So let's think about f of 2. F of 2 equals 4, right? Well, what else do we know equals 4? Because this is an even function, this is kind of the weird thing about evens and odds that are going to play into inverses today. That's the same thing as f of negative 2, right? Ooh, I guess I could throw in those, 1 second. Find that a little bit better. F of 2 is actually 2 squared, right? Equals 4 equals the same thing as negative 2 squared equals f of negative 2. Well, here we've got f of 2 equals f of negative 2, right? But what we know is 2 does not equal negative 2. And if we go and look at our definition that we kind of glossed over above about these functions, look right there. It says that if the function's y values are the same, then the function's x values better be the same. And if they're not the same, then they better not be the same. So what we've just said is we've arrived at a contradiction saying, look, the y values are the same and the x values are not the same. This is not 1 to 1. So not 1 to 1. Okay. And then this is the linear function. I mean, I guess I could allow you to learn to practice graphing a linear function. It's probably got a slope of 3, right? And a y-intercept of 4. And if you were just to guess and say, does this pass the horizontal line test? It probably does. So I will let you draw your own conclusion about that function and not define it for you. All right. That's the horizontal line test. That's the easiest way. If you can just get a good graph of that function and try that horizontal line test, you're going to be set. All right, let's see what else happens. So if you have a 1-to-1 function, that's the whole point of doing that and asking yourself if f of x does not equal if f of a does not equal f of b, or f of x1 does not equal f of 2, then x1 better not equal x2. The whole point of that is for this thing called an inverse. And an inverse function is kind of just the opposite of a function. It's really an interesting topic where normally we're taking an x, funneling it through a system, and plugging it into a y. Well, now we've said, I've just defined a function where that's 1 to 1 each time. So if you can go forward, guess what? You can go backwards with no question in your brain. So here's what we're going to do. We're going to go backwards. I think there's a typo in here I need to fix real quick. This 3 should be a 7. This 8 should be a negative 10. Fix that on the next go around on the PDF. All right, so let's just say we know f of 1 equals 5, right? So here's the definition of the inverse. It goes backwards. So if the function takes 1 and turns it into 5 through a machine or through some system, then the inverse function, which we write like this, if you look up above, the inverse function is going to take that 5, and you know what it's going to turn it into? Back into the 1. Same thing with this. If f of 3 equals 7, then the inverse is going to take that 7 and turn it back into 3. One more thing. If the f of 8 turns 8 into negative 10 through some system of equation, then the inverse of that is going to take that 10 and turn it back into an 8. That's the easiest way to look at it. Side note on that is that these are all making points, right? So here, if I draw this red line, right? So this is the function, and this is the inverse of the function, right? So the function is making a point. The function, let's just do that black text at the front. F of 1, or here, I'll just write it in text. F of 1 equals 5 is defining the point 1 comma 5, right? Because it's an x turning into a y. But when we get to this inverse, it's defining a point 5 comma 1. So what we're saying is that first point is on the graph of f of x. And that second point better be on the graph of f negative 1x, or f inverse x. Interesting tidbit that when we get to graphing, you'll see happens. So here's a table, and it's saying, hey, identify some inverses. So if we're going to do just one quick example, the inverse of 12 better equal, the inverse of 12 better equal, you take 12, you follow the arrow, and it better equal 4. Cool. And you can do a couple more of those. You can do all 5 of them to practice. Here's a graph example. Same thing, let's call it f. The inverse of, pick a number. Let's not do a green line. Let's pick something different so we can see it happen. I'm going to pick, looks like I'm going to pick 4. The inverse of 4, so what, like we said, the inverse is taking a y and turning it into an x. So I'm going to go to the y, and I'm going to look at 4, right? That's right there. So I'm going to go across. See, where does 4 hit that line? Looks like it hits it at right around 4, 5, 6. So it better equal 6. So then in my brain, if I wanted to double check, what that technically should be saying is that f of 6 better equal 4. So if f of 6 equals 4, let's go check without all my markings on there. If I go and look at this function normal style, and I look for the function 4, 5, 6, is it? Boom. It does look like it's about 4 to 6. That's how you can check. Go backwards, forwards, it should work. And I mean, just as a side note, I'll do it in blue, I guess. Does this pass that horizontal line test? Watch me go across the function. Looks like it. Never hit it twice. Okay. So now we're going to talk about, that was all the fast part. We went through that because that's pretty easy. Now we need to look at composing, or the composition of functions, when you have inverses. The whole reason about learning composition was to do inverses, right? So maybe not entirely, but mostly. I think this is a pretty important part of composing functions. So basically, if you compose a function and its inverse, you should be left with, I'll highlight it, x. And that's pretty much the whole check. So once you get done finding an inverse, be like, oh, let me compose it. If I get an x, I know I was probably right. So let's see. Let's compose these two functions. Let's go f of g of x. And actually, I should write it in the composition way that you might see someday. F of g, the little composite sign of x, equals f of g of x equals, we'll go real slow, f of, what is g of x? It's right up there, x to the 1/3 equals, now we're going to take that 1/3 and plug it in everywhere we see an x in our f function. So now I got x to the 1/3 on the inside, and what is my f function? Here, watch. If f is blue, the blue function is doing that, right? So watch this, I'll turn f blue now. F is the blue function, g is the red function in this problem. So you can see what the f of x is doing, it's that cubed, and what the g of x is doing, it's that x, the red function, x to the 1/3. And then if we just follow some algebra, side note, an important side note, the power of a power rule, x to the a to the b is the same thing as x to the ab. It is not the same thing as x to the a plus b. I get that a lot. That's the product. These two things are not the same. I know it's confusing to look at because they look so similar. Those two things are not the same. One of them is the product rule, or the product rule for exponents, because this is a product in the middle, and one is the power rule of exponents. Okay? These two things are not the same, even though they can be tricky in our brains. So when we see this, we need to multiply those two. So we will multiply x to the 1/3 times 3 up top, which technically you know is 3 over 1, so that leaves us with 3 over 3, which leaves us with x to the 1, which is the same thing as x, and that's what we wanted. So these are inverses. It's cool. It's the first inverse function we've seen. The inverse of the cubic function is the cube root function. Pretty interesting. Let's double check it reverse, though, to make sure we're true. So now we've got the red function on the outside, g of f of x, right? So then we've got red function. G is red, right? Yep. Red function of blue function of x, right? So we've got red function of, and then what is the blue function? Because now we're plugging it in, x cubed. Now we've got parenthesis to the 1/3 with the cubed in the middle this time. This is how you can kind of see that composite happening a little different, right? The red thing is doing the red functions thing on the outside this time instead of the inside. If that's confusing, maybe go back and watch the composite video. But here we go. Same exact system, same exact law that lets us do this all. And we're get back to our x. Good to go. So it's not too crazy of a system. So let's call this step 1 is green. Let's do this like a stoplight. Step 2 will be yellow, and step 3 will be red. All right, because red will be we're done. Yellow, red. Let's do orange since yellow is a little too not visible. All right, so step 1, write the function with a y instead of an f of x. Not too bad. Watch this. Step 1, y equals 3x minus 2. Might be the easiest step we've ever done. Step 2. Solve this equation for x. Okay, so solve this equation for x means get x by itself. That was from week 1 of class. So to get x by itself, we'll follow the normal steps we would always follow. Reverse PEMDAS, plus 2, y plus 2 equals 3x divided by 3, divided all by 3, and we are left with x equals y plus 2 all over 3. If you want to break that apart into y over 3 plus 2 over 3, please know those are the same thing. If it's a multiple choice test, you need to know they're the same because you don't know which one it's going to give you. If it's not a multiple choice test and you just want to know that you can break them apart, really important for you to see because you just never know what's going to be easier to plug something in to that y value. So let's see, what are we doing here? There's our function in terms of x. So now what are we going to do? I'm going to stick with that first one because it just seems a little easier. So there's our functions in terms of x, and now it says interchange x and y. Okay, so because the inverse is swapping it, right, going backwards, now we're just going to swap x and y. So this will be the red step. So that was step 2, where we solved for x, and now we're going to swap x and y. So watch this. I'm going to move all this over a little bit. Sorry about that. Boop, boop. All right, here we go. Step 3, y equals x plus 2 all over 3. I swapped x and y, and it doesn't, so it does say this. And then go ahead and rewrite it again. It says resulting in y is the inverse function. So I'm going to write the inverse function instead of y, because that's the way we're going to see it all the time. And that's the way, probably what the question asked us for. Okay? And how could you go and check that? You know how you could check that, right? So if you were going to go check it, and you should go check it, Sake of the shortness of the video, I'll pass on that right now. But you should definitely go and check that inverse, right? How would you do it? You'd go f of the inverse of x, right? And you would plug it in and do that. Okay? Not too crazy? All right, let's see what's next. Let's see what we're looking at. There's a couple inverses that you can practice. Okay, here we go, looking at graphing the inverse. Graphing the inverse is cool and really fun. So, graphing the inverse of a function. So when you're graphing the inverse of a function, we've talked about vertical reflection in class with the negative, right, on the outside of the function or on the not attached to the x. So it's outside of the square, or it's outside of the square root, or it's outside of the absolute value, or it's outside of whatever else, parentheses if you have them. We talked about inside reflections, which are horizontal across the y-axis. But sometimes you can reflect it across a line. Sometimes you can reflect it across this basic line, which is y equals x, which is the parent linear, just as review. That's that parent linear function, right? Just, I don't know, tidbit for test review. So you can reflect it across that line. And what they've done is for every single point, they draw that green line, and watch this. If I were to copy and paste that green line and put it on the other side, watch this, duplicate that, put it on the other side, boop, probably hits it perfectly on that red line. And every single point it does that. So that's just a way that you can graph it real fast. So watch this. Sketch the graph of this whole function, right? Okay. I'm drawing this thing. We know what the parent function looks like, right? Because you memorized your parent functions. That is, well, I'll say f. There's the function f of x equals the square root of x, right? So then we go back to last week and we say, what kind of shift is that? That looks like a horizontal shift, and it looks like a horizontal shift opposite of your brain. Your brain thinks negative left. Nope, it goes to the right. So it's a horizontal shift right 2. So what I'm going to do is I'm going to take that function, 1, 2, and I'm just going to plot it right here. Boom. If you want to erase that red one, you can. I'm going to leave it just so it's a little review for the horizontal shift. Just know which function we're working with, all right? So know which function you're working with at all times. All right, so there it is. Yay, we're done. Sketch a graph. We did it. Use the graph to sketch the inverse. Okay, well, here's what I'll do. I'll copy this. And now that we've practiced that, I will delete that red function so that you can kind of see just the inverse without any of that mess. All right. So now I'm going to draw the line y equals x, which is the normalist line, 1 to 1. Perfect line, right? F of x equals x. And now what we're going to do is we're going to reflect it, right? We're just going to take every point, and I know I can do this and it's a little harder for you, but I'm just going to draw a perpendicular line, and then I'm going to duplicate it and just put it on the other side. Well, that's not perfect because I noticed that one should be on the axis. So I drew it a little bad, but that one should be on the axis, right? And start right there. And if I did it from right here, boop, and I duplicate that line, I'm going to draw that point. We should be looking at that line right there. And if we did that 1,000,000 times, we'd get 1,000,000 points. And it would look like the square root function, but going up instead of down, which actually looks a whole lot like what function? Probably y equals x squared with the restricted domain from 0 to infinity. Because half of it didn't get reflected. The other half, the bottom half, the negative on the square root half, was left alone this time. So it's got a restricted domain, and that's our function, right? Oh, I found the equation. Well, let's find the equation using the formula instead of, oh wait, and it's not the regular one, it has a shift up 2, right? Look at that, that's a 2 shift. So I should have put that plus 2 there. So that's finding the equation with the graph, but now I'm pretty sure C really wants you to find the equation in your brain with the formula that it gives you. So remember step 1? Step 1 was just rewrite it as y, that's the easy step. Y equals the square root of x minus 2. Step 2, that was our yellow step. Step 2 was to solve for x. So we'll go y squared, get rid of that square root, right? And then we'll go plus 2, and we will end up with x equals y squared plus 2. Now step 3. Step 3 was to switch x and y. So now we're left with y equals x squared f plus 2. And to keep in mind, we did restrict that domain because we do know this function is only going to half of it and it's not going to the whole thing. Because when we squared that square root, right? When we squared that square root, we didn't have a plus or minus in front of the square root beforehand because that would have made it not a function. And we can go and talk about the functions and not just one-to-oneness, but passing the vertical line test as well. But we do have that function with the restricted domain because we didn't reflect this invisible half, which you would think should be there for a parabola like that. That wasn't there because our original function had to be a function and it had to pass that vertical line test. Okay. Last but not least, I'll give you we'll talk about this first model, but then we'll let you do the inverse and the plug in, chug, and all that stuff. So find a function that models the price of pizza with n toppings. So we're just going to read this problem and see. Local pizza parlor, they spend $12 for a plain cheese. So you walk in there, you want a pizza, $12 minimum, right? Cool. So you're spending $12 no matter what. $12, pizza, that's it. $2 for each topping. So if I want 6 toppings, that's going to be an extra $12. So that puts me at a $24 pizza, which is crazy. So that's how we're going to kind of look at this problem. We're going to say, okay, well, if we're looking for a function f of, what do you want to call it? Toppings, t? Is that what it says? Oh, it says n toppings. F of n, that's the number of toppings. So we know already n's our variable, right? So we say, okay, well, if it's $2 per topping, all that's going to do is add $2 per topping, so 2n. But it's not 2n because if I just go in and buy literally pepperonis, they're not going to charge you $2, right? Got to buy a pizza. It's a pizza store. So we got to pay $12 minimum. So even if we got no toppings, n was 0 and that went away, or I'll do it this way. Even if we got 0 toppings, so we just got cheese and that went away, we still have to spend that $12, right? So that's kind of where that formula kicks in. So there's our formula. And then your job is to find the inverse of that formula. So you're looking for f inverse of n, right? And then kind of figuring out, what does that mean then? Could I figure out the price of any pizza, topping-wise? And there's a blank page that's nothing. So that's inverses. That's one-to-one functions. If you have any questions, feel free to email me. Let me know. Make sure you're test reviewing. Make sure you're getting ready because we're kind of approaching as we wrap up Chapter 1. And I'm looking at the first pre-calculus test. It's going to include all of this. Actually, this is Chapter 2 that we wrapped up. All of Chapter 2 and the beginnings of Chapter 3. So thank you for watching. Let me know if you have any questions. Go back and watch the old videos. Keep reviewing. Keep studying. Keep learning what you know and what you don't know, and trying to master what you don't know. That's the most important thing I could stress as we approach test week. So I'll see you soon. See you in class. And have a great week.